So one of the things you've been a believer for a long time is scaling laws broadly defined. So are you still a believer in the
Yeah,
scaling
yeah.
laws?
Yeah, we have more scaling laws now.
So I think you've outlined four of them with pre-training, post-training, test time, and agentic scaling. What do you think when you think about the future, deep future and the near-term future? What are the blockers that you're most concerned about that keep you up at night that you have to overcome in order to keep scaling?
Well, we can go back and reflect on what people thought were blockers.
Mhm.
So in the beginning, we were the pre-training scaling law. People thought, rightfully so, that the amount of data that we have, high quality data that we have, will limit the intelligence that we achieve. And that scaling law was an important, very important scaling law. The larger the model, the correspondingly more data results in a smarter AI. And so that was pre-training. And Ilias Sutskever, Ilias said, we're out of data or something like that. Pre-training is over or something like that. The industry panicked, that this is the end of AI. And of course, that's obviously not true. Um, we're going to keep on scaling the amount of data that we have to train with. A lot of that data is probably going to be synthetic. And that also confused people, and what people don't realize is that they've kind of forgotten that most of the data that we are training, that we teach each other with, inform each other with, is synthetic. You know, I, y- it's synthetic because it didn't come out of nature. You created it. I'm consuming it. I modify it, augment it. I regenerate it. Somebody else consumes it, and so we've now reached a level where AI is able to take ground truth, augment it, enhance it, synthetically generate an enormous amount of data. And that part of post training continues to scale. And so the amount of data that we could use that is human generated will be smaller and smaller and smaller. The amount of data that we use to train model uh, uh, is going to continue to scale to the point where we're no longer limited. Training is no longer limited by data, is now limited by compute. And the reason for that is most of the data is synthetic. Then the next phase is test time. And I still remember people telling me that inference, oh yeah, that's easy. Pre-training, that's hard. These are giant systems that people are talking about. Inference must be easy. And so inference chips are going to be little tiny chips, and
Mhm.
they're not like NVIDIA's chips. Oh, those are going to be complicated and expensive, and we could make, and this is,
Mhm.
and in the future, inference is going to be the biggest market, and it's going to be easy, and we're going to commoditize it, and everybody can build their own chips, and that was always illogical to me because inference is thinking. And I think thinking is hard. Thinking is way harder than reading.
Mhm.
Pre-training is just memorization and generalization, and looking for patterns and relationships. You're reading versus thinking, reasoning, solving problems, taking unexplored experiences, new experiences, and breaking it down into decomposing it into solvable pieces that we then go off either through first principle reasoning or through previous examples, prior experiences, or just exploration and search and trying different things. And that whole process of test time scaling, inference is really about thinking, and it's about reasoning, it's about planning, it's about search, and so how could that possibly be compute light? And we were absolutely right about that. So test time scaling is intensely compute intensive. Then the question is, okay, now we're at inference and we're at test time scaling. What's beyond that? Well, obviously, we have now created, one agentic person. And that one agentic person has a large language model that we've now developed. But during test time, that agentic system goes off and does research and bangs on databases, and it goes on and uses tools. And one of the most important things it does is spins off and spawns off a whole bunch of sub-agents, which means we're now creating large teams. It's so much easier to scale NVIDIA by hiring more employees than it is to scale myself.
Mm-hmm.
And so the next scaling law is the agentic scaling law. It's kind of like multiplying AI. Multiplying AI, we could spin off agents as fast as you want to spin off agents. And so, you now have 4 scaling laws. And as we use the agentic systems, they're going to create a lot more data. They're going to create a lot of experiences. Some of it we're going to say, wow, this is really good. We ought to memorize this.
Mm-hmm.
That data set then comes all the way back to pre-training. We memorize and generalize it. We then refine it and fine-tune it back into post-training. Then we enhance it even more with test time, and the agents and agentic systems, put it out into the industry. And so this loop, the cycle is going to go on and on and on. It kind of comes down to basically intelligence is going to scale by one thing, and it's compute.
But there's a tricky thing there that you have to anticipate and predict, which is some of these components, it requires different kind of hardware to really do it optimally. So you have to anticipate where the AI innovation is going to lead. For example, mixture of
Perfect.
experts with sparsity.
Perfect.
With hardware, you can't just pivot on a week's notice. You have to anticipate what that's going to look like. And
So good.
that's so scary and difficult to do, right?
For example, these AI model architectures are being invented about once every 6 months,
Yeah.
right? And system architectures and hardware architectures kind of every 3 years. And so you need to anticipate what likely is going to happen, 2-3 years from now. And there's a couple of ways that you could do that. First of all, we could do research internally ourselves. And that's one of the reasons why we have basic research, we have applied research, we create our own models. And so we have hands-on life experience right here. This is part of the co-design that I'm talking about. We're also the only AI company in the world that works with literally every AI company in the world. And to the extent that we can, we try to get a sense of what are the challenges that people are experiencing.
So you're listening to the whispers across the industry, the AI labs.
That's right. You got to listen and learn from everybody, and have a. And then the last part is to have an architecture that's flexible, that can adapt and move with the wind. And one of the benefits of CUDA is that it's, on the one hand, an incredible accelerator. On the other hand, it's really flexible. And so that balance, incredible balance between specialization, otherwise we can't accelerate the CPU, versus generalization so that we can adapt with changing algorithms, that's really, really important. That's the reason why CUDA has been so resilient on the one hand, and yet we continue to enhance it. We're at CUDA 13.2, and so we're evolving the architecture so fast that we can stay with the modern algorithms. For example, when Mixture of Experts came out, that's the reason why we had NVLink 72 instead of NVLink 8. We could now take an entire 4 trillion, 10 trillion parameter model and put it in one computing domain as if it's running on one GPU. People probably didn't notice, I said it, but if you look at the architecture of the Grace Blackwell racks, it was completely focused on doing one thing, processing the LLM. All of a sudden, 1 year later, you're looking at a Vera Rubin rack. It has storage accelerators. It has this incredible new CPU called Vera. It has Vera Rubin and NVLink 72 to run the LLMs. It also has this new additional rack called Grok. And so this entire rack system is completely different than the previous one. And it's got all these new components in it. And the reason for that is because the last one was designed to run MOE large language models, inference, and this one is to run agents. And agents bang on tools. And
Obviously, the design of the system had to have been done before Claude Code, Codex, OpenClaw. So you were anticipating the future, essentially.
yeah,
And that comes from what? From the whispers, from the understanding what all the state of the art is.
No, it's easier than that. You just reason about it. First of all, you just reason. No matter what happens, at some point, in order for that large language model to be a digital worker, let's just use that metaphor. Let's say that we want the LLM to be a digital worker. What does it have to do? It has to access ground truth. That's our file system. It has to be able to do research. It doesn't know everything. We don't have, and I don't want to wait until this AI becomes, universally smart about everything, past, present, and future, before I make it useful. And so therefore, I might as well let it go do research. It's obviously, if it wants to help me, it's got to use my tools. A lot of people would say, AI is going to completely destroy software. We don't need software anymore. We don't even need tools anymore. That's ridiculous. Let's use a thought experiment. And you could just sit there, enjoy a glass of whiskey, and think about all these things, and it would become completely obvious. Like if I were to create the most amazing agent that we can imagine in the next 10 years, let's say it'd be a humanoid robot. If that humanoid robot were to be created, is it more likely that the humanoid robot comes into my house and uses the tools that I have to do the work that it needs to do? Or does this hand turns into a 10-pound hammer in one instance, turns into a scalpel in another instance, and in order to boil water, it beams, microwaves out of its fingers, or is it more likely just to use a microwave, And the first time it goes up to the microwave, it probably doesn't know how to use it, but that's okay. It's connected to the internet. It reads the manual of this microwave, reads it, instantly becomes an expert.
Mm-hmm.
And so uses it. And so I think I just described, in fact, almost all of the properties of OpenClaw.
Mm-hmm.
That it's going to use tools, that it's going to access files, it's going to be able to do research. It has I/O subsystem. And when you're done reasoning about it through it in that way, then you say, oh my gosh, the impact to the future computing is deeply profound. And the reason for that is I think we've just reinvented the computer. And then now you say, okay, when did we reason about that? When did we reason about OpenClaw? If you take the OpenClaw schematic that I used at GTC, you will find it 2 years ago. Literally 2 years ago at GTC, I was talking about agentic systems that exactly reflect OpenClaw today. And of course, the confluence of many things had to happen. First of all, we needed Claude and GPT and all of these models to reach a level of capability. So their innovation and their breakthroughs and their continued advances was really important. And then, of course, somebody had to create an open source project that was sufficiently robust, and sufficiently complete, and that we can all put to work. And I think OpenClaw did for agentic systems what ChatGPT did for generative systems, and I just think it's a very big deal.
Yeah, it's a really special moment. I'm not exactly sure why it captured so much of the world's attention, but it did, more than Claude Code and Codex and so on.
Because consumers could reach it.
Sure, yeah. But there's also so much of this is vibes, and Peter, I had a podcast with him. He's a wonderful human being. So part of it is also the humans that represent the thing.
Yeah,
And
no doubt.
part of it is memes and because we're all trying to figure it out. There's really serious and complicated security concerns about when you have such powerful technology, how do you hand over your data so they can do useful stuff? But then there's scary things associated with that. And we as a civilization, as individual people and as a civilization, figuring out how to find that right balance.
Yeah, we jumped on it right away, and we sent a bunch of security experts its way.
Mm-hmm.
And we did this thing called OpenShell. It's already been integrated into OpenClaw.
And NVIDIA put forward NemoClaw.
Yeah, exactly.
The install is super easy. It makes sure that it's secure.
We give you 2 out of 3 rights. Agentic systems can access sensitive information, it can execute code, and it can communicate externally.
Mm-hmm.
We could keep things safe if we gave you 2 out of those 3 capabilities at any time, but not all 3. And out of those 2 out of 3 capabilities, we also give you access control based on whatever rights that you're given by enterprise. And then we connect it to a policy engine that all these enterprises already have. And so we're going to try to do our best to help open claw become a better claw.
So you eloquently explained how we have a long history of blockers that we thought were going to be blockers and we overcame them. But now looking into the future, what do you think might be the blockers now that it's clear that agents will be everywhere? So it's obviously we're going to need compute. So what is going to be the blocker for that scaling?
Power is a concern, but it's not the only concern. But that's the reason why we're pushing so hard on extreme co-design, so that we can improve the tokens per second, per watt, orders of magnitude every single year. And so in the last 10 years, Moore's Law would have progressed computing about 100 times in the last 10 years. We progressed and scaled up computing by 1,000,000 times in the last 10 years. And so we're going to keep on doing that through extreme co-design. So energy efficiency, perf per watt, completely affects the revenues of a company. It affects the revenues of a factory, and we're just going to push that to the limit so that we can keep on driving token costs down as fast as we can. Our computer price is going up, but our token generation effectiveness is going up so much faster that token cost is coming down. It's coming down an order of magnitude every year.
So power, that's an interesting one. So the way to try to get around the power blocker is to try to, with the tokens per second per watt, try to make it more and more efficient. Of
Yeah.
course, there's the question of how do we get more power?
We should also get more power.
That's a really complicated one. You've talked about small modular nuclear power plants. There's all kinds of ideas for energy. How much does it keep you up at night? The bottlenecks in the supply chain of AI, like ASML with EUV lithography machines, TSMC with advanced packaging like CoWoS, and SK Hynix with high bandwidth memory.
All the time, and we're working on it all the time. No company in history has ever grown at a scale that we're growing while accelerating that growth. It's incredible.
Yeah.
And it's hard for people to even understand this. In the overall world of AI computing, we're increasing share. And so supply chain, upstream and downstream, are really important to us. I spend a lot of time informing all the CEOs that I work with, what are the dynamics that's going to cause the growth to continue or even accelerate. It's part of the reasons why, to the entire right-hand side of me, we're CEOs of practically the entire IT industry upstream and practically the entire infrastructure industry downstream.
Mm-hmm.
And there were several hundred CEOs. And I don't think there's ever been keynotes where several hundred CEOs show up. And part of it is I'm telling them about our business condition now. I'm telling them about the growth drivers in the very near future and what's happening. And I'm also describing where are we going to go next so that they could use all of this information and all of the dynamics that are here to inform how they want to invest. And so I inform them that way, like I inform my own employees. And then, of course, then I make trips out to them and make sure that, hey, listen, I want you to know this quarter, this coming year, this next year, these things are going to happen. And if you look at the CEOs of the DRAM industry, the number one DRAM in the world was DDR memory for CPUs in data centers. About 3 years ago, I was able to convince several of the CEOs that even though at the time HBM memory was used quite scarcely, and barely by supercomputers, that this was going to be a mainstream memory for data centers in the future. And at first it sounded ridiculous, but several of the CEOs believed me and decided to invest in building HBM memories. Another memory was rather odd to put into a data center is the low power memories that we use for cell phones. And we wanted them to adapt them for supercomputers in the data center. And they go, cell phone memory for supercomputers?
Mm-hmm.
And I explained to them why. Well, look at these two memories, LPDDR5, HBM4. The volumes are so incredible. All three of them had record years in history, and these are 45-year companies. And so, that's part of my job is to inform and shape, inspire,
So you're not just manifesting the future and maybe inspiring NVIDIA, the different engineers of the company. You're manifesting the supply chain of the future. So you're having conversations with TSMC, with ASML,
Upstream, downstream,
upstream, downstream. So that's the thing.
GEV, Caterpillar. Yeah, that's downstream from us.
Yeah.
See? Yeah. There you
Yeah,
go.
the whole thing. I mean, but
Yeah.
there's so much incredibly difficult engineering that happens in the entire semiconductor industry. And it's just feels scary how intricate the supply chain is, how many components there are, but it works somehow.
Exactly. The deep science, the deep engineering, the incredible manufacturing, and so much of the manufacturing is already robotics. But we have a couple of hundred suppliers that contribute the technology that goes into our 1.3 million component rack.
Mm-hmm.
Each rack is 1.5 million components. There are 200 suppliers across the Vera Rubin rack.
So it's interesting that you don't list that as the thing that keeps you up at night in the list of blockers.
But I'm doing all the things necessary to,
Okay.
yeah, see? I can go to sleep because I checked it off. I said, okay, I can go to sleep and I go, well, let's see let's reason about this. What's important for us?
Mm-hmm.
Let's reason about this. Because we changed the system architecture from the original DGX1 that you remembered to NVLink 72 rack scale computing.
Mm-hmm.
What does that mean? What does that mean to software? What does that mean to engineering? What does that mean to how we design and test? And what does that mean to the supply chain? Well, one of the things that it meant was we moved supercomputer integration at the data center into supercomputer manufacturing in the supply chain.
Mm-hmm.
If you're doing that, you also have to recognize you're going to move one. And if your total footprint of whatever data center you're going to build, let's say you would like to have 50 gigawatts of supercomputers that are running simultaneously, and it takes 1 week to manufacture that 50 gigawatts of supercomputers, then each week in the supply chain, the supercomputers are going to need a gigawatt of power. And so we're going to need the supply chain to increase the amount of power it has to build, test, and test the supercomputers in the supply chain before I ship it.
Mm-hmm.
Well, NVLink 72 literally builds supercomputers in the supply chain and ships them 2-3 tons at a time per rack. It used to be they used to come in parts, and we used to assemble them inside the data center. But that's impossible now because NVLink 72 is so dense. And so that's an example. And I would have to go into, I'd fly into the supply chain, go meet my partners, and hey, I said, guess what? So here's what I'm going to do with this is the way we used to build our DGXs. We're going to build them this way. This is going to be so much better because we're going to need them for inference. The market for inference is, coming. The inflection point for inference is coming. It's going to be a big market. And so I first explain to them what's going on, why it's going to happen. And then I ask them to make several $1 billion of capital investments each. And because they trust me, and I'm very respectful of them, and I give them every opportunity to question me, and I spend time to explain things to people, and I reason about it. I draw them pictures, and I reason about it in first principles. And by the time I'm done with them, there's know what to do.
So it's a lot of it's about relationships and building a shared view of the future.
Yeah.
But do you worry about certain bottlenecks? I mean, what are the biggest bottlenecks in the supply chain? Are you worried about it? ASML's EUV tooling? Are you worried about the packaging, CoWoS packaging of TSMC? About how fast it could scale? Like you said, you're not only growing incredibly fast, you're accelerating your growth. So it feels like everybody in the supply chain, and those are certainly bottlenecks, would have to scale up. Are you having conversations with them? Like, how can you scale
All
this
the time.
faster? Do you worry about it?
No.
Okay.
Because I told them what I needed. They understood what I need. They told me what they're going to go do, and I believe what they're going to do.
Interesting.
Yeah.
That's great to hear. So maybe if we can just linger on the power for a little bit, what are your hopes for how to solve the energy problem?
One of the areas, Lex, that that I would love love us to talk about and just get the message out. You know, our 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 power grid is designed for the worst case condition with some margin. Well, 99% of the time, we're nowhere near the worst case condition because the worst case condition is a few days in the winter, a few days in the summer, and extreme weather. Most of the time, we're nowhere near the worst case condition, and we're probably running around, call it 60% of peak. And so 99% of the time, our power grid has excess power and they're just sitting idle. But they have to be there sitting idle because just in case, when the time comes, hospitals have to be powered and, infrastructure has to be powered and airports have to run and so on and so forth. And so the question that I have is whether we could go and help them understand and create contractual agreements and design computer architecture systems, data centers, such that when they need the maximum power for infrastructure in society, that the data centers would get less.
Mm-hmm.
But that's in a very rare instance anyways. And during that time, we either have our backup generators for that little part of it, or we just have our computers shift the workload somewhere else, or we have the computers just run slower. We could degrade our performance, reduce our power consumption, and provide for a slightly longer latency response, when somebody asks for an answer. And so I think that way of using computers, of building data centers, instead of expecting 100% uptime and these contracts that are really, really quite rigorous, it's putting a lot of pressure on the grid to be able to, now they're going to have to increase from their maximum. I just want to use their excess.
Mm-hmm.
It's just sitting there.
Yeah, that's not talked about enough. So what's stopping there? Is it regulation? Is it bureaucracy?
I think it's a throughway problem. It starts with the end customer. The end customer puts requirements on the data centers that they can never not be available. Okay, so that the end customer expects perfection. Now, in order to deliver that perfection, you need a combination of backup generators and your grid power supplier to deliver on perfection. And so everybody's got to have 6 nines. Well, I think first of all, right now, we ought to have everybody understand that when the customer asks for these things, you have somebody in your data center operations team disconnected from the CEO. I bet the CEO doesn't know this. I'm going to talk to all the CEOs. The CEOs are probably not paying any attention to the contracts that are being signed. And so everybody wants to sign the best contract, of course. And they go down to the cloud service providers and the two contract negotiators that are, I could just see them now, negotiating these multi-year contracts. Both sides want, the best contract. As a result, the CSPs then have to go down to the utilities and they expect the 6 nines. And so I think the first thing is just make sure that all of the customers, the CEOs of the customers, realize what they're asking for. Now, the second thing is we have to build data centers that gracefully degrade. And so if the grid tells us, listen, we're going to have to back you down to about 80%, we're going to say that's no problem at all.
Mm-hmm.
We're just going to move our workload around. We're going to make sure that data is never lost, but we can reduce the computing rate and use less energy. The quality of service degrades a little bit. For the critical workloads, I shift that somewhere else right away, so I don't have that problem. And so, whichever data center still has 100% uptime. And so,
how difficult of an engineering problem is that, the smart dynamic allocation of power in the data center?
As soon as you could specify, you could engineer it.
Beautifully put.
So long as it obeys the laws of physics on first principles, I think we're good.
What was the third thing you were mentioning?
So the second thing is the data centers. And the third thing is we need the utilities to also recognize that this is an opportunity. And instead of saying, look, it's going to take me 5 years to increase my grid capability, if you're willing to take power of this level of guarantee, I can make them available for you next month and at this price. And so if utilities also offered more segments of power delivery promises, then I think everybody will figure out what to do with it. Yeah, but there's just way too much waste in the grid right now. We should go after it.